So what I'll be doing today is I'll be taking up the problem set number 5 for side 111, and this is going to be covering linearization, Newton's method, taking limits, a bit of L'Hopital, and then the mean value theorem. So let's get started. So our first question goes as follows. So find L1 at x, and what this means is that you want to find the linearization of the function, which we're going to get, which is f of x is equal to 3 3x squared minus 2x plus 1 for an x value of 1. Okay, so before we get started, let me just quickly review what linearization really means. So what I'm going to do is I'm going to draw a graph right over here, bam, and let's say we have some sort of function. So there you go, we have some sort of function, perfect. And now what linearization does is I'm going to say at this point on this function, so let's call this A, point A, what I'm going to do is I'm going to draw a line through it, which is going to have the same slope as on A. So there you go. That's not quite the same slope. So let's just quickly adjust that. As we all know, I'm not the best at the actual drawing. Okay, so there you go. We have the same line built with the same slope at A. And the reason you want to do this is because that can help us approximate the points near A. You can be saying, well, Max, how do you know that this is going to approximate the points near A? Well, the whole point of constructing this line is that near A, since this line has the same slope as the function at A, the growth of this line is going to mimic the growth of this function, just because it has the same slope. Now, as you get further and further along the function, we're going to see that the slope doesn't reflect the rest of the function. But at near this point, A, this line is going to be very, very close to the function itself. Okay, and so to get this line, what we're going to do is if we have this function f of x, so let's say, well, we have f of x here, so just not to confuse ourselves, we're going to have g at x, so at g at x. So at this point A, what we're going to do to find this line is we're going to say, so to find a line, we need the slope and a point, basically. And so our point then is going to be A, f at A, so that's our point, and then our slope is going to be f prime at A. And so then if we use our slope point form to write our line, we're going to get y minus A is equal to, or sorry, y minus f prime, f at A is what I meant to say, f at A is equal to f prime at A, which is the slope, times x minus A. So then if we simplify that a bit, we're going to get y is equal to f at A plus f prime at A x minus A. And so this is the linearization of g of x at A. Now let's go back to our question. What we have in our question is we need to find the linearization of this f of x at 1. So what we first need to do is we need to find the derivative of f of x. So if we take f prime of x, we're going to get 6x squared minus 2. And then what we need to do to find it at 1, because that's where we're trying to find a linearization, we're going to plug in 1, so we're going to get 6 times 1 minus 2 equals to 4. And so if we get 4, we can then find all the rest of it. So the only real information we need is our f at A. So if we plug 1 into our function, we're going to get 3 times 1 minus 2 plus 1. And that is going to give us 2. So 3 minus 2 plus 1 is 2. Perfect. And now we have all the information we need. So L1 at x is going to equal to 4. That's my f at A. Plus f prime at A. So that's going to be 4. And I mistook here. This is 2 because f at A is 2. Plus 4, which is f prime at A, times x minus 1, because that's where our point is at. And there you go. We have our linearization for the function f of x. Now, b for this function, what it does is it asks the following. So now find L0 at x. So again, that means find linearization for x equals 0 for the function g of x, equals to e to the negative x squared plus arc tan 3x. So what are we going to do? Well, the first thing we need to do is we need to find the derivative for g of x. Because again, if you remember, the linearization L0x is going to equal to g at 0 plus g prime at 0, x minus 0. So again, let's find g prime at 0. G prime. Let's just find g prime first, then we can find g prime at 0. So g prime at 0, we're going to start off with e to the negative x squared. And so what we're going to have here is our chain rule. So it's going to be equal to e to the negative x squared. We're going to chain it to negative x, the derivative of negative x squared. So times negative 2x. Now we're going to take the derivative of arctan of x. And that is going to be plus 1 over 1 plus 9x, and that's 9x squared, because the derivative of arctan is, so arctan, the derivative of arctan is going to be equal to 1 over 1 plus x squared. And the reason this is the case is, I'm going to quickly just go through this. So if we're looking for the derivative of arctan, what we can say so let's start. So y. So y equals to r tan of x. So then we can say that tan of y equals to x. So then if we want, we can take the derivative of both sides. And we just do need to remember that we are going to be implicitly deriving this. So then on the right side, what we get is the derivative of tan is secant squared to be exact. So it's going to be secant squared of y. Now, because it's y over here, we're going to multiply it by dy dx, and then equals to x. The derivative of x is 1, so it's going to be 1 over here. So then we're going to get dy dx is equal to 1 over secant squared y. And now 1 over secant squared is just cosine. So it's dy over dx equals to cosine squared of y. And now y, you can later on try to replace it. You know that y is equal to arctan of x, but if we just place arctan of x, that's not going to be too helpful, is it? So now what we're going to do is instead is we're going to visualize y as some sort of angle in a triangle. What we're going to do over here is we're going to say that this is x over 1. So then if we draw a triangle, so here we're going to draw a triangle. Bam. So we're going to call this y. And now we know that tan of y is x over 1. So we're going to get x over here and 1 over here, because that would be tan of y. And then we can try to calculate our hypotenuse by just Pythagorean theorem. So hypotenuse squared is going to be equal to square root of x squared plus 1. And then if we're trying to get, finally, if we're taking cosine squared of y, so now we can see what cosine squared of y is going to be. And cosine squared of y is going to be adjacent over hypotenuse. So it's going to be 1 over square root of x squared plus 1. And if you take that squared, the squared is going to cancel out on the bottom, giving us 1 over x squared plus 1. And there you go. That's how we get root of arctan. So again, if we go back, it's 1 over 1 plus 9x squared, because we're going to square the root. And then we can't forget the chain rule. So times 3. Perfect. Now what we're going to do is we're just going to find g prime at 0. So at 0, all of this cancels out because 0 times anything is 0. So then on this side, what we're going to get is 1 over 1 plus 9 times x squared is 0. So 1 over 1 is 1 times 3 is 3. So g prime at 3 is in fact just 3. So then what we need to do, just before we need to get g at 0. So g at 0, we're going to get e to the 0. This is 1. And then arctan at 0 is 0. So this is just going to be equal to 1 at 0. So g at 0 equals to 1. So then finally, for our linearization equation, we get L 0 at x is equal to 1 plus 3 at x. Perfect. Let's move on to question 2. Now, question 2 reads, estimate the value of cube root of 28 and cube root of 26 using an appropriate linearization. Compute the error in your estimate by comparing your approximation with the actual values of cube root 26 and cube root 28. And so let's do it. So what are we thinking of? We are thinking that f at f at x is equal to cube root of x. There it is. So now what's going to happen is we want to linearize this. And the closest number basically to root 28 and root 26, and this is cube root and cube root is going to be 27. 27 is a really nice number, like right in the middle of them. That's what we're going to use. We're going to have our linearization at 27. So L at 27 is equal to f at 27 plus f prime at 27 times x minus 27. And so let's calculate this. So first we need to calculate f prime. So f prime at x is going to equal to 1/3 of x to the power of negative 2 over 3 equals to 1. Let's make that a bit nicer. So 1 over 3 times cube root of x squared, or you can put the squared on the outside. So then if we calculate that at 27, we're going to get equals to 1 over 27, because you're going to get cube root of 27 is 3. 3 squared is 9. 9 times 3 is 27. Cool, let's plug everything in. So then f at 27 is just 3. So it's 3 plus 1 over 27 times x minus 97 equals to, so x over 27, 1 over 27 times 27 is just negative 1. So 3 minus 1 is 2. So it's x plus x over 27 plus 2. And so then what we're going to get is, we're going to have to plug in our numbers now. And so that's what I'm going to do. We're just going to plug into this equation our two numbers. So the first number is we're trying to get 26. So we're going to go right into our calculators, 26 over 27 plus 2. And so for x equals 26, we are going to get an approximation of 80 over 27, which is then equal to 2.962, repeating. Then we're going to get x is equal to 28. And in this case, we're just going to plug it in, 28. So at x equals 28, we're going to get, it's going to be 82 over 27, which is the same thing as 3.037. Now the actual cube roots of 26 is, so the actual cube root of 26 is 2.9 equals to 2.9624. So it kind of starts differing on the fourth decimal here, 26. And then the cube root of 28 is equal to 3.03655. So here it kind of starts differing already on the fourth as well. And so what do we see? Well, we actually see that these two differ by different margins. What did I do? That these two differ by different margins. You're gonna, if you look at it, they're compared a bit differently. And this actually makes sense if you think about it, because if we draw the graph, as weird as it sounds, if we draw the graph of the cube root, it's a lot steeper than the square root. It's gonna level out a lot faster, but that means that 27, let's say 27 is over here, 27. What we do is if we build the linearization point, again, as we know, I'm terrible at drawing these lines, even though I have a literal tool that helps me make them straight. But the basic gist of it is that over here, because it's already a bit steeper, in theory, the 27 should be, the 28 should be a bit closer than the 26, because here, at this point, the slope is going to be a bit smaller than 26. And over here, the 28 is going to be even a bit smaller than the 27. So because of that, because it's gradual as well, the 28 is going to be a bit closer to the actual approximation than the 26. Hopefully that makes sense. Okay, let's move on now to the question 3. And in question 3, what we're going to be doing is we're going to be developing Newton's method for estimating the root of an equation. That sounds pretty cool. So before we actually discover it, I actually just want to explain it to you, and then we're going to go on our discovery. As funny as that sounds, we're going to first learn it, and then we're going to go on the discovery. So what the Newton's method basically does is if we have a function, let's say this is our function. Even better, I'm just going to make it a bit easier for us. I'm going to make it cross only over here. Nope, I don't like this. Let's make it go like this. There you go. So what the Newton's method says is that we're going to pick some point that is near our zero. And the way we can figure out where about our zero is using the intermediate value theorem, which states that if I know that over here it's in the negatives and then over here it's in the positives, then I know that in between those two values, you're going to have to cross all of the values possible. But basically using that, we can kind of get close to where we should start. But then what we're going to do is we're going to start somewhere. So let's say we start at point A. So from point A, what we're going to do is we're going to draw straight line. We're going to linearize at point A. So at point A, we're going to linearize. And from that linearization, this line will cross 0 at some point x1. So then I'm going to draw onto my function just a bit more. So let's say it goes like this. So then when the 0 drops at x1, we're going to drop that and we're going to see so if this is f of x, then at f at x1, what we're going to do is we're going to draw another linearization from f at x1. So if we draw another linearization of f at x1, bam, what we're going to see is that it intercepts the x-axis now at some point x2. So then what we're going to do is we're going to take this x2, we're going to bump it up, and over here we're going to get f at x2. And then we're going to build a linearization from f at x2. Let's make this one red just so we can see it a bit better. So if we build a linearization at f at x2, it's going to go something like this. And what you'll notice is that with each of these approximations, we're getting closer and closer to that 0. And that's basically what Newton's method is that the more lines you're going to draw, the closer you're going to get to that 0. Cool. So now let's kind of think of it let's try to discover this in a bit of a different way. So let's do it. So what we're going to do is we're going to get y equals f at x, and we're going to begin with some point x0. So if we linearize at x0, what's going to happen is we're going to get L at 0, or at x0 to be more exact. You can't just say it's at 0. L at x0 of x is going to be equal to f at x0 plus f prime x0 times x minus x0. Now, perfect. Now, this line x0 is gonna, what is it called? It's gonna intercept the y-axis on some point x1. And so, not the y-axis, I meant the x-axis. It's gonna intercept the x-axis at some point x1. So then, what we can do is we are going to say that. So then what we're going to do is we're going to say Lx1 is at 0. So it's going to intercept, the x-intercept is going to be x1. And so then, well, the new function, as I'm going to say, we have to kind of go down at x1. So then what we're going to, so again, this, sorry, probably that was a bit confusing because I wasn't really saying anything, but this is x1, right? So we found our x-intercept. So the next thing is we're going to build a linearization at f at x1. So the linearization of at Lx equals to x1 is, it's going to be f at x1 plus f prime at x1 times x minus x1. So what's going to happen then? What's going to happen then is that what's going to happen then is that we can, I skipped a step and that's why it's confusing me and everybody as well. So what we're going to do is what we're going to do is as I said, we're going to solve for f at x equals to 0. So what I'm going to do, I'm going to make this a bit less confusing. I'm going to take up exactly Newton's method, and I'm going to take up this question specifically in another video. So then question 4 and question 5 deals with Newton's method, and again, I'm going to take that up in another video. I guess when I'm a bit more prepared to explain, yay, let's go into L'Hopital's rule. But again, what it's going to come down to is this. I wasn't quite able to explain it well right now. So let's go into question 6 then, and that's going to be using our L'Hopital rule. So L'Hopital rule, just for everybody who doesn't remember, is that if you have limit x as it approaches a, if you then get a function where if you plug in a, it's going to, for instance, we have x minus a over x squared minus a squared. If both of these are reaching 0, then what you can do is you can take the derivative of top and bottom. So let's see how that works out for us. So we're going to get, let's start with the first one. We're going to get limit as x approaches 1, root of x minus 1 over x squared minus 1. And so then what we do is we're going to plug in 1. We're going to see that 1 minus 1 is 0. And on the bottom we have 1 minus 1 is 0. So that means we can use L'Hopital rule. And so if we use L'Hopital rule equals to LH, which means L'Hopital rule. So we're going to take the derivative of the top and the derivative of the bottom. So we're going to get the derivative of the top is 1 over 2 root x. On the bottom, it's going to be 2x. Then if we simplify that, what we're going to get is 1 over 4 root x. Oh, sorry. We're going to get is 1 over 4 root x. 1 over 4 root x. And then if we were to plug in x equals to 1, what then we would get is 1/4. So that would be our limit. Okay, let's look at the next question. And the next question is limit as x approaches 0 plus 4 root of x ln x. And so over here, what we see is that if we just plug in x, what we're going to get is 0 times 0. But that's not an indeterminate case. And because of that, what we need to do is we're going to kind of artificially make it an indeterminate case so we can use L'Hopital. So what we're going to do here is this is equal to ln x over 1 over root of x. And so that, if you think about it, it's the same thing here. If you plug in 0 plus, this is going to infinity, and because root of x is going to 0, 1 over 0 is infinity, and so it's infinity over infinity, so it gives us a good thing. And over here, when I said 0 times 0, I meant to say 0 times infinity. And now what I really do recommend is you put the ln x on top, because if you put the ln x on the bottom, it's not really going to really help you cancel out the ln x and get rid of it, which will make it very hard. So just let's do it like this. And now we can use L'Hopital rule. So LH. So we're going to take the derivative of the top. It's going to be 1 over x. We're going to take the derivative of the bottom, which is going to be, you can think about it as, I'm just going to put it as inside x to the power of negative 1/2. If you take that derivative, it's going to be equal to negative 1/2 x to the power of negative 3 over 2. So that's 1/2. We're going to have negative 1 over 2 x to the power of 3 over 2. Cool. So now that we have that, this is going to be equal to, it's just equal to 1 over x times negative 2x times 3 over 2. And then the x and x over 3 and x 3 over 2 is going to kind of cancel out. 3 over 2 minus 1. So we're just going to get negative 2 root of x. And then if we plug in 0, we're going to get a 0. So that's our limit for this one. It's just 0. Okay, let's move on to the next one. And the next one is limit as x approaches infinity for x over ln of 1 plus 2e to the power of x. First thing we're going to do is what happens when we plug infinity. So if we plug in infinity, it's going to be infinity over ln at infinity is still going to be infinity, so it's going to be infinity over infinity. Therefore, we can use L'Hopital, so LH for the L'Hopital, the hospital. That joke, I don't know. So we're going to take the derivative. It's going to be 1 over 1 over 1 plus 2e to the x. And then we chain it to what's inside, so times 2e to the x. So then that is going to equal to 1 times what is it? 1 plus 2e to the x over 2e to the x. Now, if we plug in infinity, it's still going to be infinity over infinity. So this is, again, an indeterminate case. So then we're going to take L'Hopital again. And then what we get is just going to be 2e to the x over 2e to the x, which is then equal to 1, because that simplifies. As an aside note, what you could do is over here, you could simply simplify it. Instead of taking L'Hopital, what you could do is you could simplify it then to be something which you don't need to take L'Hopital of, just by doing this. So it would be, if you, what is it called? What you can do is you can simplify it so that it isn't L'Hopital by taking out 2e to the x on top. So if we take out 2e to the x on top, we're going to get, or even better, let's go like this. We're just going to take e to the x out on top. So if we take e to the x out on top, it's going to be e to the x 1 plus e to the, it's going to be 1 plus, it's not 1 plus, there you go. It's 1 over e to the x plus 2 over 2e to the x. The e's to the x cancel out here. So we're going to get e to the negative x plus 2 over 2. And then if you plug in infinity, e to the negative infinity is just 0. So then it's still going to equal to 1. Cool. Let's go on to our fourth limit. That's d. So d, we're going to get limit as x approaches 0, 1 minus 2 to the 1 minus 2x to the power of 1 over x. And that is equal to, so what we're going to do here is we are going to use, what we're going to do is we are going to basically ln both sides. The way you can think of it is like this. So if we have f of x is going to have a limit of L, ln f of x is going to have the limit of ln L. And in the end, what you can do is that f to the x is going to have the limit, is going to have the limit of e ln to the L. And so in theory, you could just cancel out the E and the ln to the L. But the whole point of the ln is that we get rid of this 1 over x on top to make life easier for us. So if we do it, then we're going to get limit of x to the 0. And it's going to be 1 over x. So if we take ln of everything, it's going to be 1 over x times ln of 1 minus 2 to the x, just like that. And so if we think about it a bit further, we actually get our indeterminate case, which we like, because this can be viewed as ln 1 minus 2 to the x over x. And so on the bottom is going to be 0. On the top it's going to be 1 minus 0, and ln of 1 is just 0. So then we get our indeterminate case. Then what we can do is we can take L'Hopital, so LH. So on the bottom, it's just going to become a 1. On top is going to become 1 over 1 minus 2x, and then you have to chain it to negative 2. So then this is going to just equal to negative 2 over 1 minus 2x. So if we place 0 in right now, what we're going to get is negative 2. And if you thought we were done, that's a big psych, because we're not quite. Because remember, now what we have to do is we found ln L. We found ln L. The ln of the limit is negative 2. So now f of x has the limit of e to the power of negative 2. And that's going to be our limit. Cool. Let's go on to the 7th question now. So question number 7. So question number 7 says, show using the definition of the derivative f, oh, sorry. First it says, consider the function. Consider the following. F of x is equal to, oh, that was a terrible bracket. Now my pencil, it was so terrible, my pencil stopped working. That's not good. There, it started working again. Okay, there you go. So it's going to equal to sine x over x, where x does not equal to 0, and then it equals to 1 when x does in fact equal to 0. And so it says, show using the definition derivative that f is differentiable at x equals 0. So the definition of the derivative is limit as x approaches some a, and in this case it's 0. We're going to get f at x minus f at 0 over x minus 0. And in this case, what's going to happen is we can now try to evaluate. So f at x is sine of x over x. Sine of x over x. F at 0 is 0, so minus 0 over x minus 0. And that is equal to sine of x over x over x. So then that's just going to become, now I made a mistake here. Hopefully some of you spotted. F at 0 by our definition is going to be 1. That's why I was getting confused, because it didn't quite match up with what I did before. So it's going to be sine of x over x minus 1 over x. So then that's going to be equal to sine of x minus x over x squared. And that's just going to be, if you make this one into x over x, and then you would bring the x up, so you would get sine x minus this. Okay, then what you can do is there's two ways of doing this. The first way is just taking L'Hopital, because you get 0 over 0. The second way is you can just simplify it like this. So you could say sine x squared minus x squared, and then you can try going from here as well. But the simpler way is to just take L'Hopital, because everything simplifies quite nicely then. So if you take L'Hopital here, you're going to get cos of x minus 1 over 2x. And the reason you can take L'Hopital is because you have 0 minus 0 over 0. Now what we'll notice that again we have an indeterminate case here because cosine 0 is 1. So 1 minus 1 over is 0. So 0 over 0 is to 1. So again we can take L'Hopital. If we take L'Hopital, we're going to get negative sine x over 2. And then sine at 0 is 0. So this is just all going to equal 0. So then we get that the derivative at this is just going to be equal to 0. Perfect. Now what we're going to do is we're going to read the second question. Yay! And the crowd goes wild. So find f prime at x for x does not equal to 0 if is fx continuous at x equals to 0. So let's write that down. So we need to find f prime at x for x does not equal to 0. And then what we need to do is we need to figure out that is f prime at x continuous at 0. And everything looks big. There you go. Now everything should look a bit better. Find f at x. So firstly, f at x, f prime at x, so that is going to be sine x over x. So if you want to take the derivative of that, it's going to be our quotient rule. So we're going to get x times cos of x minus sine x over x squared. And so that's our derivative. Now, to show that something is continuous at 0, we're going to need to take the left side limit and the right side limit and shows that it equals to what's in it. So we know that at f prime at 0 is 0 from the previous example. So now we just need to show that the left side limit and the right side limit are equal, or just that the limit when it's going there is 0. So let's do that. So limit as x approaches 0 of x times cos x times cos x minus sine x over x squared. So in this case, what we have is we have an indeterminate form. So what we can do is we can just take L'Hopital. So let's do that. We're going to take L'Hopital equals to LH. So on the bottom, we're going to get 2x. On the top over here, it's going to be a product rule. So that's going to be cos x plus negative sine x. So that's what I'm just going to remove it and say negative x sine x. And then over here, the derivative of sine x is cosine x, which would be negative cosine x. So negative cosine x and cosine x cancel out. X and x cancel out. And so we're going to be left negative sine x over 2. And we know that that is just going to be 0. And so it is continuous because the limit approaching 0 is equal to what it equals at 0, what the function equals at 0. And therefore it's continuous. So the next question then is, drumroll please, it's question 8. So that's what goes after 7. Woo! The crowd goes wild again. So the next question is 8. And it just says find the absolute maximum and minimum values for f at x equals to 6x to the power of 4/3 minus 3x to the power of 1/3 for the interval -1 and 1. And so here what we're basically going to be doing is we're going to be finding our critical numbers. Then we're going to be checking our edge cases as well, because it could happen, right? So if we have a function that looks like this, right? So then our edge case, like the bracket, is going to be our maximum. So that's why we need to check these two as well. So let's just find f prime x. That is equal to, so it's going to be equal to 8x to the power of 1/3 minus x to the power of -2/3. I'm going to factor out, yeah, it equals to that. So I'm going to factor out x to the power of -2/3 out, just to make things a lot easier to work with. So if I factor out x to the negative 2/3 out, x to the power of negative 2/3 out, what's going to happen is we're going to get 8x minus 1. That's a 3. And yeah, this is just really nice to work with. So then we get some critical numbers here. So the numbers we need to check are x is equal to 1 over 8. Then over here, at this point, it's x equals to x at 0 doesn't exist because remember this is 1 over 0, but the actual function does exist at 0. So therefore, this is also a critical point that we need to check. So x equals to 0 is a critical point. And then we need to check x equals to negative 1 and x equals to 1. And from these, we can find what our local maximum and minimums are. So if we plug all of this in, the points that we should get is x at 0 is 0. That's pretty easy to see. X at 1/8 is just going to be negative 9 over 8. X at negative 1 is 9. And x at 1 is 3. This is f at x, I mean, for all of these. So then we get our local maximum and minimum, absolute, which is negative 9 over 8 is going to be our minimum at 1 over 8. And our maximum is going to be 9 at negative 1. Perfect. So let's go on to the next question, which is 9. A certain roller coaster in the shape of the curve y equals e to the negative x squared, where x is greater or equal to 0. The most exciting moment is the point where the slope is the steepest, at which point x, y on the track does this occur? So let's try to look at this then. So y equals to e to the negative x squared, or x is greater than 0. So now, just before we start quickly, we are looking for the most exciting moment is the point where the slope is the steepest. So we're looking for at what moment is the slope the steepest. So in a way, what we're looking for is when the slope is the biggest. So now, our first derivative, so f prime at x, basically shows us what the rate of change is for our function. So the rate of change for a function. Now, the second derivative, what that will show us is the rate of change of the function. So we could see basically how big our rate of change is and at what places. So you can also think of it like this. We use the first derivative to find our maximums and our minimums for the function itself. Because based on that, based on how it's growing or descending, we can tell how much our function is growing or descending. So we can use the second derivative as the first derivative for first derivative and then see where that is going to be the biggest and the smallest. And because we're looking for basically the biggest our f prime can be, that's where we're eventually going to be taking the second derivative. So let's do it. So f prime at x is going to be equal to e to the negative x squared, chain it to negative 2x. So that's our first derivative. But again, we're looking for our second derivative because the second derivative will tell us when our first derivative is the biggest. We're going to have the steepest slope in essence. So then what we get is f prime at x is equal to, so here we're going to have the chain rule because we have x over here. So it's going to be, not the chain rule, I meant the product rule. So it's going to be e to the negative x squared times negative 2x times negative 2x. So this negative 2x is the chain rule for the negative 2x, and then this negative 2x is from here, plus e to the negative x squared times negative 2. So let's simplify that a bit by taking out, so negative, okay, first I'm just going to rewrite it. So it's going to be 4x squared times e to the negative x squared minus 2 e to the negative x squared. Now I'm just going to factor out negative 2 ex e to the power of negative x squared. It's going to be negative 2 ex to the power of negative squared. So e to the power of negative x squared bracket. So here it's going to be 1 minus 2x squared. Here it is. So e to the power of negative x does not equal to 0. Oh, it equals to 0 when x is equal to infinity, but we can't really analyze that. But then over here, we know that it's going to be x is 0 when it's plus or minus 1 over root 2. So then we know that the negative one can't be because we're only considering x's which are greater than or equal to 0. And so that means that the steepest slope will be at x is equal to 1 over root 2. And what that basically means in terms of our first derivative is if we have, okay, here, let me show you on decimals, because I think that would be the best way to visualize this. So here we have our function, so f of x is equal to e to the power of negative x squared. So there you go, this is our function. So now what we're going to see is in our first derivative, what we see is how our function itself, and I'm just going to check that I have the right function, e to the negative squared, negative x squared. Perfect. So here what we see is that this shows how this function rises and falls basically. So from here we have the slope climbing. So at this point, I assume we have an inflection point then somewhere here. Then it starts descending. And at this point we have another inflection point, and then it starts going up again. And this just shows us how our function then, how its slope is. So from here to here, it's always getting bigger. But then at this point, the rate of change starts to decline, right? So the slope is still positive, but then so here, while the slope is getting bigger, at this point over here, the slope starts getting smaller again. And then here it becomes negative, so the function starts decreasing, and then it stays negative, but then over here, again, it starts increasing. So then if we take f prime prime of x, then what we see is how our second derivative, if we just look at our first derivative, how that looks like. So then we get here is these are our critical points where the first derivative starts increasing or decreasing, right? So here it's growing, 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 growing. It's positive. Then over here, what we see at 0 point here, at this point, our first derivative starts decreasing. And then it's going down, down, down. And there you go. And this is negative 1 over root 2, which is what we got. So yeah, so we see that at this point exactly is when our function starts decreasing, because this is, again, just the way it works. And hopefully that made it more clear. So now let's go on to question after 9, which is, trouble please, question number 10. Oh, and the crowd goes wild again. I have so much energy, don't I? So consider, let's read the question. We just did 9. Consider f at x. Consider the following. Consider f at x is equal to x cubed plus 4x plus 1. Show that the equation f at x equals 0 has exactly one solution. So show that f at x has exactly one solution, only one. So what we're going to do first is we're going to just show that it has at least one solution. What we're going to do is we're just going to employ the intermediate value theorem. So if I plug in 0 for here, what I'm going to get is, so f at 0 equals to 1. Then if I plug in f at negative 2, what I'm going to get is negative 8 or minus 8. So yeah, I can even plug in negative 1. Let's do that quickly. So at negative 1, f at negative 1, that is going to equal to f at negative 1 is equal to f at negative 1 is equal to negative 1, negative 5, negative 4. So negative 4. So in between negative 1 and 0, we know that it crosses 0. So we know it has at least one solution. Now the next step is proving that it only has one solution. The way we're going to do that now is we're going to take the derivative. It's f prime at x is equal to 3x squared plus 4. Now this function, it only grows. And we know that because this is always greater than 0. So that means slope is always positive. And that means that even if this function started at negative infinity, it only ever grows. So it can only ever pass 0 once. And that's how we know then that it only passes once, because if it's always increasing, then it can only go through it once. And there you go. Question 10. That's it. And the question after question 10 is 15. No, I'm just kidding. It's not 15, it's 11. Even though we're all tired, we're not that tired, hopefully. Okay, you're driving on a straight highway on which the speed limit is 100 kilometers per hour. At 8 a.m., a police car clocks your velocity at 100 kilometers per hour. At 8:04, a second police car posted 9 kilometers down the road clocks your velocity at 100 kilometers per hour. Explain why the police has a right to charge you with a speeding violation. Okay, let's quickly draw this. So here we have our dandy car, bam, and we're just cruising along 100 kilometers per hour. So over here, we're gonna say that there's a policeman. Okay, there, we're just gonna draw it with sirens, and it's flashing sirens. And he, at exactly 8, they saw us going 100. And we drove a bit further. You can show us driving. Bam, we were driving, we were driving, we were driving. And then at this point, there was another police officer, and he saw us at 8:04. He saw us again going 100 kilometers per hour. And the question says, well, that police officer can give us a ticket. And how does he know that he can give us a ticket? So the reason the police officer can give us a ticket is the following. So let's assume that our position is a function of time. So s at t. So then s at 0. So we're going to say that this is where we started. S at 0 is equal to 0. We traveled 0 distance. Then s at 1/15, because we're going to consider this an hour, and so 1/15 of an hour is 4 minutes. So s at 1:15 is equal to then 9 kilometers. I guess I forgot to write that, so the distance between them was 9 kilometers. So then what we're going to do is we're going to use the mean value theorem, and we're going to say that f prime I mean, not f prime. In this case, we're using s, so it's going to be s prime of t is going to equal to, so then we're just going to do it, so s at 1/15 minus s at 0 should equal to, not over 1/15 over 0, and then that is equal to 9/0 over 1/15, which is equal to 135. So my speed at some point had to be 135. And that's how he knows that he can get me a ticket. Now, question 12, which says two runners try to race at the same time and finish in a tie, prove that at some time during the race their velocities must have been equal. It's very similar to this question. And the two times you basically have is that at the start of the race, they started together, and at the end of the race, they ended together. And so there you have your 2 points. And then using that, you can again use mean value theorem. I'm not going to go through it. I'm just a bit lazy because question 13 is quite tough. So this time I am just going to say that what's after question 11? Oh, look at us. It's question 13. Wowee. Look at us. Okay. So suppose that f prime prime exists everywhere. That's the question. On an interval I, which contains 0 and 2. So we have 0 and 2 with f at 0 equaling to f at 1 equaling to 0. And then f at 2 equals to 1. Now we have to prove 3 things. A, that there exists such an A that belongs to I, so in between 0 and 2, such that f prime at A is equal to 1/2. And what I'm going to do here is I'm just going to employ the mean value theorem. I'm going to say that f prime A is going to should be equal to f at 2 minus f at 0 over 2 minus 0, and then we're going to get 1 minus 0 over 2 minus 0 is equal to 1/2. Yeah, that's proved, because we know that that means that this has to be on that interval. So then B, beep, beep, that's B. So the second thing says there exists such a B for range I such that f prime at B is bigger than 1/2. And so what we're going to do for this question is the following. So what we're going to do is we're going to take two things. So we're going to do, so we're going to say, we're going to create two letters. Look at us. So we're going to say there's an M, and then there's an N. So we're going to take two intervals here. We're going to say there's an interval 0 to 1 and an interval 1 to 2. So f prime at M is equal to, it has to equal to at least once, f at 1 minus f at 0 over 1 minus 0. And so this is just going to equal to 0 because it's going to be 0 over 1. And then f prime at n, which is going to be the interval 1 to 2, is going to equal to f at 2 minus f at 1 over 2 minus 1. That's just going to equal to 1. So now what I'm going to do is now we can again apply the mean volume theorem and say that in between those two ranges, what's going to happen is that f prime prime at e, so that's the second derivative of those ranges, because we know that in the first derivative, those 2 points are going to be in between 0 and 2. So in between those 2 points, we're going to have f prime at n, f prime at n, so that's going to be the later point, minus f prime at m, that's a terrible m, f prime at m, over n minus m, and that's going to be, so f prime at n is 1, f prime at m is, f prime at m is 0. So we're going to get 1 over n minus m. Now, we know that n minus m is always smaller than 2. And the reason we know that is because we know that n is smaller than 2 and m is smaller than, is in between 0 and 1. So 2 minus, like, if we know that this is in between 2 and 1, and this is in between 1 and 0, then this just has to always be smaller than 2. So then, since we know that this is smaller than 2, we then know that f prime at b has to be greater than 1 over 2. Hopefully that made sense, because we're going to get, since n minus m is smaller than 2, fb has to be greater than 2. Okay. Now we're going to look at question C, the final one. And C, there exists such a C that belongs to I, such that, oh, my handwriting is getting worse and worse. There exists such a C that belongs to I, such that f prime at C is equal to 1 over 7. Now what we're going to do here is we're just going to kind of do, like, use what we knew before, and that is that f prime at m, if we remember from before, that was 0, and then f prime at n was equal to 1. And so using the intermediate value theorem, we know that from 0 to 1, it has to cross all the values, which then in fact will cross 1 over 7. And that's how we can guarantee that f prime at c at one point will in fact equal to 1 over 7. Okay? And so I will just give us like 3 seconds to enjoy ourselves after that hard work, I guess. Yeah, and so I will upload the Newton's theory part of this, or the Newton's methodology, in a better explanation soon as well. And hopefully you enjoyed the rest of your day.